Let's get started with lecture 32. So last time we derived a couple of important equations. So one was we found what happens if you, let's say, refract as you go across a flat interface. So if you have an object here, and you have these rays, and let's say they kind of refract away from the normal. So I don't know, in this case n2 is smaller than n1. You're going to find an image over here that's kind of closer to the interface, and if this distance is s, this is s prime. We found that s prime over s in the limit of small angles is n2 over n1. We also found the thin lens equation. So for, let's say, a converging lens with focal length f, we found if the object is a distance s away from the lens, we get an image on the other side at the distance s prime such that 1 over s plus 1 over s prime is 1 over f. In this case, these are all positive numbers. S is on one side, so the object is on one side for a converging lens, and the image forms on the other side. F is a positive number. That's how we derive this equation. Okay, let's go back here to the slides. All right, so here's a quick question. Pause the video, try to find the answer. All right, so this lens produces an inverted image on the screen on the other side. And the question is, what do you see on the screen if the lens is removed? So what would we see? Yeah, so the rays from different points just reach the different points of the screen, right? So if you have, let's say, from this one point, let's say I get a whole bunch of rays that are emitted from, let's say, this point here, right? They go in all different directions, and there's nothing on their way, so they will reach all the different points of the screen. So from every point of the object, we have light that reaches every point of the screen, and then we're not going to get an image, right? The shape of the object kind of gets lost in there. So yeah, so the lens is quite important in focusing the rays that move in all different directions but come from one point. It focuses all of them on one point. Okay, here's another question. Again, pause the video, try to find the answer. So again, we have this lens, it forms an image. What will you see on the screen if a piece of dark paper is lowered to cover the top half of the lens? So what happens? So if I think about, let's say, the image of one point belonging to this object on the screen, there are many rays, right, that are emitted, they reach the lens at different points. They bend, and then they all bend in such a way that they end up at the position of the image. So if you cover part of the lens, you get rid of part, or if you cover half of the lens, you get rid of half of these rays. But all the other half that reach the lens will bend and arrive at the image. So nothing should happen to the image except it gets slightly dimmer, right? So that's kind of an important observation, right? So you can form, let's say I cover the top half. Let's say here I have this lens and I have this object here. And if I cover that half, again, you have rays that kind of bend this way, right? Arrive at the lower half of the lens and bend and reach the image. So we're not going to lose the image there. Okay, here's another question. Again, pause the video, try to figure out the answer. So we're basically covering pretty much all of the lens except we leave a small hole. So what should happen there? Again, you know, it's the same story. It gets much dimmer because you're covering pretty much all of the lens. But again, that region in the middle is enough to support the image. So kind of in this limit, the size of the lenses is not relevant, right? Again, you have rays reaching that area, the open area of the lens from all parts of the object. Here's another quick question. So again, pause the video. So we have the object is a distance s, and the question is s larger than the focal length, equal, or smaller? So how do we figure out the focal length? Well, we see like this ray at the bottom, right? This one seems to be parallel to the optical axis. So then it must be going through the focal point. So from here to here we have F, from here to here we have S. So S must be larger. And when that's the case, of course, we form a real image. So let's talk a little bit about the signs of these quantities. So in the figure we drew, right, we put S kind of on this side of the focal point. So S was larger than F, and they were all positive numbers. The image was formed on the other side. Let's just draw a different case. So the case we drew before, right? We had converging lens, S larger than F. So what we had was, let's say F is here, here. If I put my object over here, this is gonna go there. And then, so we find the image over here. Now, let's consider the same scenario. Here's the optical axis. Here's the focal point. And then I put this object kind of closer. So S is smaller than F. Okay, so then what happens? Well, I have this. And then if you draw this, so this is one ray, right, going this way. If you draw this ray parallel to the optical axis, it goes through the focal point. And now because you see this distance, right, is longer than this distance here, these lines don't cross on this side, but if you trace them back, they would cross on this side. So in this case, we're going to get a virtual image. So the image seems to be behind the lens where there is no light. You have to trace them back. It's not a real image. But the equation we derived, 1 over s plus 1 over s prime is equal to 1 over f, still works. Interestingly, if you just solve this, you find a negative number for s prime. So see, s is positive, f is positive, and s is smaller than f. So 1 over s is larger than 1 over f. So that gives a negative number for 1 over s prime, and s prime is going to be a negative number. So positive s prime real image, negative is virtual. So this real image forms on the other side, right? And the virtual image, the rays kind of diverge, even though it's a converging lens. If you put it too close, they don't converge on the other side. If you trace them back, you can form an image. And now see here, this image is not inverted, right? So this virtual image kind of looks like that. Whereas here, this real image got inverted. Okay. Yeah, so that's what we discussed. Now, there is a quantity called the lateral magnification, m, which is defined as minus s prime over s. So remember when we were talking about the size of the image, we found that let's say if I form this image here, let's say here I have a height h, here I have a height h prime. We found that if you don't worry about the signs, h prime over h is s prime over s. Now, in this case, where s prime and s are negative numbers, if we define m to be minus s prime over s, m becomes a negative number. So not only it tells you what the size is, that negative sign indicates that it's inverted. Whereas in this case, if you construct minus s prime over s, s prime is negative, s is positive, this is a positive number. Again, m times the size of the object gives you, if you take the absolute value of m, multiply it by the size of the object, gives you the size of the image. And because m is positive, it tells you that the image is not inverted. So m is known as the lateral magnification. Okay, so yeah, so that's the picture we just studied, right? If you put the object kind of between the lens and its focal point, if s is smaller than f, then we form this virtual image. on this side, and it's not inverted. Okay, let's take a look at an example to get more practice with this. So it's looking at a flower with a magnifying glass. So we have a magnifying glass with a 6 centimeter focal length, and we hold it 4 centimeters from the flower. So the flower is closer to the lens than the focal length. We're going to get this virtual image, and it's going to be bigger. So we want to find the magnification. We want to see how large the image is. Okay, so the equation I should use is the same equation like the thin lens equation. So let's do that. So we have 1 over s plus 1 over s prime is 1 over f. So s is 4 centimeters, right? So we have 1 over 4 plus 1 over s prime is 1 over 6. That's the focal length. So let's solve for s prime. We're going to find that 1 over s prime is 1 over 6 minus 1 over 4. That's 2 over 12 minus 3 over 12, so that's minus 1 over 12, right? So s prime becomes minus 12 centimeters. So that means that the image is virtual. It's on the same side as the object. It's a consequence of tracing back the physical rays, not a place where physical rays actually converge. And the magnification is going to be m is minus s prime over s. So it's going to be 3. So the image is 3 times bigger. It's not inverted. It's a positive. M is a positive number. Okay, so that's just what we have from tracing the rays, and that's the result of the calculation. We solve for s prime. It's going to be minus 12 centimeters, and the magnification is just minus s prime over s. And the fact that this is a positive number means that the image is not inverted. Okay. So we can apply exactly the same formula to diverging lenses, except you have to put a negative number for f. That's all there is to it. So instead of these rays moving that way and converging the distance f, they converge like at minus f. They converge on this side. Again, they have a virtual convergence over here. So yeah, and if you have light like that, which would converge on the other side, you get parallel rays. And the third law is simple, is again the same. If you go through the center, you don't bend. So this equation that we found, 1 over s plus 1 over s prime is 1 over f, works for both converging and diverging lenses, except for diverging lenses, we have to enter a negative number for f. All right, so here's a quick question. We have these lights that these rays are incident on a diverging lens, so we want to see how they look like after they leave the lens. So yeah, so it seems they're if the lens weren't there, they would converge at its focal point. So then the divergence should make them parallel to the axis. So to summarize what we found, we just add something else to this table of signs. So we already argued that a positive s prime implies a real image, and negative s prime implies a virtual image. S, we always take it to be positive. It's the distance from the lens. And then f is positive for converging lens and is negative for a diverging lens. All right, so this is the end of section 34.5 on ray tracing. Basically, the summary is really just this equation, which relates the position of the image to the position of the object and the focal length of the lens. And we also have the definition of the magnification, which is minus s prime over s. And then we have to be careful about what these signs mean about whether the image is real or virtual, or the sign of f is determined by whether the lens is converging or diverging. All right, so we're done with all the new material that I wanted to talk about in this course. So this section on ray tracing is the last section we discuss. So I want to spend some time kind of reviewing the entire course, and maybe the best way is to just start with the sample final exam. So this is a real final exam from last year, and it's good to go over it. I posted it a couple of days ago, so hopefully you've had a chance to take a look at the question. So kind of the exam will be similar to homework. So I think it's good to first start with this sample exam, and then maybe just we can take a look at the list of topics. So summary slides at the end of the slides correspond to the different chapters. I think it's a useful thing to look at. And then basically the best review is reviewing the homework assignments. All right, so here is the sample exam. So let's start with the first question. So we're going all the way back to chapter 12, where we talked about things like moment of inertia, rotational dynamics, etc. Okay, so we have a dumbbell-shaped object. We have two equal masses. So mass m here, mass m here, connected by a rod of negligible mass and length r. Okay. Now, if I1 is the moment of inertia of this object with respect to an axis passing through the center of the rod and perpendicular to it, and I2 is the moment of inertia with respect to an axis passing through one of the masses over here. So let's say I have I1 around this axis, I2 around that axis. Which of the statements is correct? A, B, C, or D? Sorry, there are two B's here. All right, so it's a question related to the parallel axis theorem, right? Remember, we had I around an axis that's a distance D from an axis going through the center of mass. So let's say center of mass, we have ICM, and then you have another axis, a distance D from it. We had I is D squared M plus ICM. So the moment of inertia around the center of mass is the smallest, and around the different axes is going to be larger. So yeah, so that's the answer. To get more practice, let's also calculate these things, right? So what is the moment of inertia around the center of mass here? Well, the moment of inertia, remember, was sum over I m I r I squared. So here, if you have this axis, you have two masses, each m, and each is a distance r over 2 from that axis. So it's going to be 2. So I1 around the center of mass axis is 2 m r over 2 squared, which is 1/2 mr squared. If I want to calculate I2, well, this mass is a distance 0, so it doesn't contribute. This mass is a distance r, so I just get mr squared, and it's twice that. And we can also check that our equation works. So I2 must be the total mass, which is 2m, times the distance between the two axes, which is r over 2 quantity squared, plus I1, I center of mass. And that works. This is mr squared over 2, so mr squared over 2 plus mr squared over 2 gives us mr squared. Okay, let's take a look at the second question. So we have a tire rolling along a road without slipping. Center of mass has velocity v. There is a piece of tape attached to the outer edge of the tire. When the tape is at the same height as the center of mass, so it's either here or here, its speed with respect to the road is what? Okay. So remember, rolling without slipping means the point of contact is an instantaneous axis of rotation. Like instantaneously, it looks like everything is rotating around that point. So let's say I have a radius r. Here, this distance from here to here is going to be square root of r squared plus r squared. So that's square root 2 times r. And then we can write, let's say here we have, let's say, v prime, right? So I can write v prime is square root 2r times omega, and v is r times omega. Omega is the angular velocity. Then we find that this is square root 2 times v. So it has a larger speed. And if you look at this point, again, it's the same, right? The velocity is going to be in that direction, but the distance is, again, square root 2 times r. And both of those points that are at the same height as the center of mass have the same speed. Okay, let's take a look at the next question. So we have a mass m attached to an ideal massless spring, and when the system is set in motion with amplitude a, it has period t. Okay. What is the period if the amplitude of the motion is increased to 2a? Right, remember, amplitude is irrelevant, right, when it comes to the period. The period is just is determined by the mass and the spring constant. So it should still be t. Right, what was the period? We can quickly calculate it, right? So remember, the acceleration, yeah, so if x of t is, let's say, the amplitude cosine omega t plus some phase constant, the velocity becomes minus a omega sine of the same thing. And the acceleration is the next derivative, so a of t is minus a omega squared cosine omega t plus phi naught. So the acceleration is minus omega squared times x. And we know from F equal ma and the fact that the force is minus kx, A is minus k over mx. So just to remind you what omega was, it was the square root of k over m. And t, the period, is related to omega by omega is 2 pi over t. So t is 2 pi over omega, and that's 2 pi square root of m over k. Anyway, so yeah, so if you have a different problem where, mass or the spring constant change, we can figure out from this dependence what happens to the period. Okay, the next problem, next multiple choice question, is saying we double only the amplitude of a vibrating ideal mass and spring system. And what happens to the mechanical energy of the system? So mechanical energy, remember the energy is the kinetic energy plus the potential energy. And when, so let's say you're oscillating between minus A and A. So when you're over here at x equals 0, all the energy is kinetic. Here, all the energy is potential. So the maximum potential energy is equal to the maximum kinetic energy, and it's equal to the mechanical energy. So this is equal to 1/2 k A squared. So for a constant spring constant, k, if we double the amplitude, we should increase the energy by a factor of 4. Okay. All right, let's take a look at the next question. So it's saying the figure shows the displacement y of a traveling wave at a given position, right? So this is the first one at a given position as a function of time. That's a history graph. And the displacement of the same way at a given time as a function of position. So this is a snapshot. It's fixed time as a function of position. This is a history graph, fixed position, fixed x as a function of time. And we want to figure out how fast the wave is traveling. We want to figure out the speed of the propagation. So remember that the information we can extract from this, from a history graph, we can look at the periodicity and extract the period. From this, we can extract the wavelength from a snapshot. And we know that lambda is v times t. We know v is therefore lambda over t. Okay, so let's see if we can extract the period and the wavelength. So if I want to read off the period, for example, I can pick one full cycle starting from here, going around, coming back here. So from 3 to 7 seconds, so that's 4 seconds. Lambda, if I want to extract it, it seems, okay, so if I pick a cycle, it goes from 1 to 3, so that's 3 meters. And therefore v becomes 3 over 4 meter per second. So that's 0.75. That's the correct answer here. All right, next multiple choice question. So what is it saying? We have a transverse wave traveling on a string stretched along the horizontal x-axis. The equation for the vertical displacement y of the string is given by that expression. All quantities are in SI units. What is the maximum speed of a particle of the spring? Or the maximum speed is closest to which number? So this is not asking about the speed of propagation of the wave. It's asking about the physical speed of a point belonging to the string. So So basically, if, it's the derivative of y with respect to time is going to give me an expression for the velocity as a function of position and time, and we want to find its maximum. So let's say we know y of x and t, right, is that thing, 2 cosine pi 15x minus 52t. And then v, the velocity at x and t, is the derivative of this thing with respect to time. So derivative of cosine is minus sine, and then the argument of the cosine, if I take the derivative with respect to time, I get a factor of minus 52 times pi. So minus 52 and the minus sine cancel each other. So it's going to be 52 pi times 0.002 times sine of the same thing. And you know that the sine is between -1 and 1, and it does realize those values at some time, right? The time, if suppose you look at some position, time just keeps increasing, so there's going to be some value of time where the sine becomes 1, for example, or -1. We're asking about speed, so we just take the positive value. So this maximum speed that we want is going to be that coefficient in front of the sine. So whatever that is, let's say 52 times pi. So I'm going to need a calculator to figure this out. So that's 2 over 1,000. Let's see if we can guess what it is. So pi is 3 times 3.14. So 6.28 times 52. So let's say, let's say we say it's 3.14 times 104. So I want to take a guess and say it's 3 point something, slightly more than 14 times 100. And then divided by 1,000. So it seems A should be the correct answer, approximately. So it's 4% of 3 times 14. Yeah, that sounds reasonable. So yeah, I think A is the correct answer here. Yeah, I just double checked that with a calculator. Yeah, so up to 2 significant digits, it's 0.33. That's the number you get if you multiply these things. Okay. So next question. So 2 strings, identical material radius, are stretched with the same tension, with their ends fixed. One string is 8 millimeters longer than the other. Okay. Waves on these strings propagate at 420 meters per second. The fundamental frequency of the longer string is this, 528 hertz. What is the beat frequency when each string is vibrating at its fundamental frequency? Okay, so that's an interesting question. So let's try to digest the information we have. So we have 2 strings, identical material radius stretched at the same tension. That immediately tells us that the speed of wave is the same, right? Remember, the speed of wave was square root of tension over the linear mass density. So identical material, identical radius, it makes the linear mass density the same. The tension we know is the same, so the speed is the same. So one of them, and they're fixed at both ends. So when we're thinking about the fundamental frequencies, it's the longest possible wavelength, shortest possible frequency, so that we have nodes at the end, right? That's what it looks like. So we have strings that's slightly shorter, we have one that's slightly longer. And we know the the frequency of the longer one, so this one has f naught equal 528 hertz. So we want to figure out the fundamental frequency of this other ones, and then their difference is the beat frequency. Okay, so let's think a little bit about this. So we know the speed of propagation, we know the frequency of one, and we know the difference between length, so we're going to know the difference between the wavelength, right? Because the length is just half the wavelength in each case. So we know the difference between the two wavelengths, we know the speed, we know the frequency of one, and then we want to figure out the difference between the frequencies. So kind of we need to use the speed to relate the wavelength to frequency. So the general relationship we have, right, relating wavelength and frequency is lambda times the frequency is the speed. Okay. So let's see. So let's call this as lambda 1, this is lambda 2. And what we know is lambda 2 is going to be v over this f, so it's going to be 420 over 528, and that's in meters. And we know lambda 1 is so see, let me write an equation here before doing that. So what we know is, we know that half of lambda 2, so lambda 2 over 2, which is this length, minus half of lambda 1, which is this length of the other string, that's 8 millimeters. So that's 8 times 10 to the minus 3 meters. Which means lambda 2 minus lambda 1 is 1.6 times 10 to the minus 2 meters. So we know the difference between the two wavelengths. And we know the wavelength of one, so we can find the wavelength of the other. So let's do that. So we find lambda 1 is going to be this number minus that. So it's 420 over 528 minus 1.6 times 10 to the minus 2. Okay, so if you find lambda 1, let's say we label this fundamental frequency, we can find the fundamental frequency associated with the other one and find their difference. So f01 is going to be the speed divided by lambda 1. So I think at this point I probably want to use a calculator. So okay, so let's look at some. So let's say, so this is going to be v divided by lambda 1, right? So it's v divided by lambda 1, which is 420 divided by lambda 1. Okay, so what is lambda 1? Let's calculate it. So I have 420 over 528 minus 0.016. Okay, so that's going to be this number over here, 0.779 meters. Okay. Now we want to divide 420 by this. So let me find its inverse and multiply by 420. So it gives me 539 hertz. And then the beat frequency, which is the difference between these two frequencies, is going to be 11 hertz. Okay, let's do number 8 as well, and then I think we can do the rest of the exam in a different video. Okay, so here we have a column of gas, open in one end, close the other end. And we're talking about the fundamental resonant frequency, so the largest possible frequency. That means the smallest possible frequency, the largest possible wavelength. So it means in this entire system we fit a quarter of the wavelength, right? We want to have a note here and an antinote there. So we know 1.3 is lambda over 4. So lambda is 1.3 times 4 meters. And then we know the frequency, we want the speed, so we know the speed is lambda times the wavelength times the frequency. So it's going to be 1.3 times 4, that's in meters, times 80, which is in hertz, so that's good. Our result is going to be in meters per second. So what is that? So 4 times 80 is 320, and then 0.3 times that is 96, so we want to add 96 to 320, so that's 416, which is one of the answers. Okay, that's a good place to stop. So I'll post another video where we do 4 more multiple choice questions, and then we have 4 free response problems to work out.